Alright, today we're going to look at the combustion analysis for empirical formulas. So if we want to find the empirical formula of an unknown compound, we can use combustion to indirectly find this empirical formula. So here would be a typical example. I have an unknown compound made up of carbon, hydrogen, and oxygen. 1.621 grams of that compound. And I know that when I combust it, I produce 3.095 grams of carbon dioxide and 1.902 grams of water. So the first thing we might want to do is to write out the combustion reaction. And you'll notice that I have letters here in place of the subscripts because we don't know what numbers go with this compound. We just know that it's carbon, hydrogen, and oxygen. So we're putting X, Y, and Z. And we know that it reacts with more oxygen, and it produces the CO2 and the water. And we know the mass of the products and the mass of one of the reactants. Now our first step is to convert the carbon dioxide and the water to moles. So how do we go about doing that? We start with 3.095 grams of carbon dioxide, and then I'm going to use the molar mass of carbon dioxide. Now I got the 44 because there's 12 grams of carbon in a mole, and there are 16 grams of oxygen in a mole. And since there's 2 oxygens, I did 2 times 16, which is 32, plus an additional 12, and that gave me 44 grams per mole. If I take this number 3.095 and divide it by 44, I get 0.0703 moles of carbon dioxide. Okay, and then I'm going to do the same thing for water. 1.902 grams of water divided by 18 grams per mole, because this is the molar mass of water. Okay, and again we found that on the periodic table, and then that gave us 0.106 moles of H2O. Now, we don't want to just know the moles of carbon dioxide. I really want to just get to carbon. The unique thing that I can do is, because carbon dioxide is the only product that has carbon in it, I can assume that 100% of the carbon that came from this reactant went to the carbon dioxide. So I'm going to work backwards and find out how many moles of carbon are in the carbon dioxide. And if I know how many moles of carbon dioxide or carbon are in the carbon dioxide, I know how many moles of carbon I started with. So I'm going to come over here and I'm going to say let's get this a little higher, 0.0703 moles of CO2, and I'm going to use dimensional analysis, and I'm going to say in 1 mole of CO2 there's 1 mole of carbon, because that's the ratio, right? It's 1 to 1, which means that I basically have 0.0703 moles of carbon. So if I produced this many moles of carbon, I started with that many moles of carbon. So now I already have the first mole in my empirical formula calculation. Now I need to find the moles of hydrogen and the moles of oxygen before I can go back to our normal problems where we divide by the smallest number and look for the whole number ratios. So the next thing I'm going to do is I'm going to take my moles of water, 0.106 moles of H2O. Now I can't go straight here with the water because I'm looking for hydrogen. And again, I can do the same thing because hydrogen in water is the only source of hydrogen. So therefore, all of the hydrogen in water is all of the hydrogen we started with. Okay? So I can assume that however much hydrogen I have in the water is how much hydrogen I have in this compound. So I can say 0.106 moles of water. In 1 mole of water, now this is a little different, there's 2 moles of hydrogen. Because if we look at the chemical formula, for every 1 water molecule, I actually have 2 hydrogen atoms. So this becomes a little different than the carbon one. Okay? So 0.106 times 2, and I end up with 0.212 moles of hydrogen. So now I know how many moles of carbon I started with and how many moles of hydrogen. So the last thing I have to find is how many moles of oxygen I started with. Okay? So how do you think we might go about doing that? Well, the best way to do it is through understanding that we know how many moles of carbon and hydrogen. What if we went back to grams? Not grams of carbon dioxide, but grams of carbon. Then we would know how many grams of carbon we had and how many grams of hydrogen, and we know how many grams total. We could figure out how many grams of oxygen were in this molecule. So we're going to work a little backwards. Okay? And we're going to start with the moles of carbon. So we had 0.0703 moles of carbon. And we know that in 1 mole of carbon, there's 12 grams. So this number times 12 is equal to 0.844 grams of carbon. That's how much carbon contributed to this 1.621 grams of my total sample. So I'm going to do the same thing with the hydrogen. 0.212 moles of H. In 1 mole of H, there's 1 gram of H. And so this is equal to 0.212 grams of hydrogen. So now I'm going to take the initial mass of the substance, 1.621 grams, and I'm going to subtract out the mass of the carbon, and I'm going to subtract out the mass of the hydrogen, and the difference should be the grams of oxygen. So when I do this, I get 0.565 grams of oxygen. Hopefully you saw how I did that. Okay? Mass of carbon here, mass of hydrogen here, and then I subtracted it from the total mass of the compound. This was HYOZ. Remember, this is what we started with. Okay? Now that I know the mass of oxygen, I can find the moles. So 0.565 grams of oxygen. There's 16 grams of oxygen in 1 mole, and so this becomes 0.0353 moles of oxygen. Now if we go back, we had already calculated that there was 0.0703 moles of carbon, and there was 0.212 moles of hydrogen. Now look what we have. We have moles of elements, which is what we can now use to calculate the whole number ratio in an empirical formula. So remember, we find the smallest number. So in this case, that's going to be the 0.0353. So we're going to divide each number by 0.0353, divided by 0.0353, divided by 0.0353. This is equal to 1. This is equal to 1.99, which is pretty much 2, and this is equal to 6.00, which is equal to 6. So now we have 2, 6, and 1. So our empirical formula is C2H6O, and of course we don't put the 1. Hope that helps. Best of luck to you.